In this module, what we're going to do is review probability and random variables. And so remember that the whole reason that we have a probabilistic or statistical framework is the fact that there's uncertainty in the world. If you do an experiment or make an observation of a temperature, and if you go back and then look at it a little bit later, even though the conditions haven't changed, you might find that you get a slightly different value. And really that's a reflection of all sorts of random fluctuations in the world around us. And so when we talk about probability, remember we're talking about a circumstance or an experiment where we have outcomes. And so for example, if I'm talking about the color of cars, then I might have a red car, I could have a green car, I could have a blue car, and I could have a gray car, for example. And so each one of those is an outcome. What we need to be able to do is to say, we might have a situation where what we're interested in is a collection of outcomes, so some sort of an event. And so we have the idea of an event. And so, for example, I could think of this event E1, so this is an event. And event E1 might be that the car is not blue. Well, if the only colors that cars can be are red, green, gray, and blue, then the event not blue means that it's either red, gray, or green. So that's just a reminder that we have both elementary outcomes, and then we have events that are collections of outcomes. Remember that we have a measure of this. And so we have the concept of probability. And what probability does for us is it says, what's the relative frequency with which different outcomes or different events occur? And by relative frequency, really what we mean is, what's the chance or the likelihood that these things occur? And so probability then is a measure. It's a way of sort of measuring the likelihood of outcomes. And remember that probability has to satisfy a number of different rules. So if the set of all outcomes is what we would call the sample space, so this would be S, the set of all outcomes, then the probability that S occurs, i.e. the probability that something occurs, had better be 1, okay? And remember that the probability is between 0 and 1, so that's our second rule, right? So that the probability has to be between 0 and 1 because it's a relative measure of frequency of occurrence. And so just like chemical engineers would say that a mass fraction or a mole fraction has to be between 0 and 1 by definition, similarly, because we're talking about relative fractions, the probability has to be between 0 and 1. So the probability that something happens has to be 1. And then the other basic rule that probability has to obey is that if I have two mutually exclusive events, E1 and E2, the probability of E1 and E2 happening has to be the probability of E1 plus the probability of E2. And that's where E1 and E2 are mutually exclusive, meaning they can't happen together. Okay. So these are what are sometimes referred to as the axioms of probability, these three rules here. Okay. From those three rules, we know that the probability of nothing happening, okay, so that's nothing, happening is 0, which is kind of the companion of the probability of something happening. So if the probability of something happening is 1, the probability of nothing happening is 0. Something always happens. And another thing that's very useful that we might use is that if we have an event E, then we can use the notation and put a bar over it, and this means not E. And so what we can find is that the probability of E happening, the probability of an event happening, is equal to 1 minus the probability that the event didn't happen. And so that's a trick that we also use quite often as well. So if we stop for a minute, or pause for a second, what we've done so far is we've said, in the world around us, outcomes happen. Different colored cars, for example, could be temperatures instead. What we've then said is, okay, we need a way of thinking about the individual outcomes, and we need a way of thinking about collections of outcomes happening. The concept of collections of outcomes is an event, and we can talk about individual outcomes, and then we can have the set S of all outcomes. We have a way of trying to measure how often certain things happen relative to other things, and that's the probability. It has to follow a few rules. And so now we've got the probability framework. The last thing I want to do in this particular module is to talk about random variables. And random variables are an invention, if you want, where what a random variable does is it attaches a numerical value to an outcome. And so if I went back to that red, green, blue, gray kind of situation there, so if I start again where I've got this sample space and it's red, green, blue, and gray, then what a random variable does is it says, for each one of those outcomes, that random variable is going to attach a numerical value. And so what X might do is say that if the car is gray, then that random variable value is going to be 4. And if the car is blue, then X would say that that random variable value is 3. And so maybe red, it's going to have a random value, variable value of 1, leaving maybe green is going to correspond to 2. So the point about it is that in one sense, random variables attach numerical labels. Typically, though, what we do is we say we've got a random variable, it's got numerical values, we can talk about a probability distribution or a probability density function for these things. But the concept of a random variable is to allow us to work with things in a quantitative, i.e. numerical, kind of a way. So that's the thing I really wanted to touch on for random variables. We're very used to working with random variables that just inherently describe situations where numerical values occur. And so an example of that is if I'm talking about temperature, we know that temperature takes on a continuum of values. And so it takes on a continuum of values on the real line. Okay. And so there's 0. Temperature will take on a continuum of values along the real line. Now, it's not really limitless, is it? Because we know that temperature can't go below absolute 0. So strictly speaking, temperature is a real valued random variable that goes from absolute 0, so for example, minus 273 Kelvin, through to, it can approach an infinite temperature. And so it's very naturally a continuous random variable, but we would still have the idea that we've got a temperature random variable, and maybe that one we'll use the symbol T for, and it takes on numerical values. So just to recap the concept on random variables, we very naturally just start working with random variables. The thing to remember is that a random variable is a way of sticking a numerical label on outcomes. Sometimes you don't really need it because the values are already, the outcomes are already numerical, but in other cases you might actually need to.